Okay, so welcome everybody to this new edition of this quantum seminars supported by the Quantum Spain. And today is my pleasure to present you Martin Ringbauer from the University of Innsbruck. In fact, he's one of our collaborators in all these things related with quantum technologies. And today he's going to talk about the quantum simulation with trap ions in qudits. But his background, his thesis, more or less, has a short, long story. He was born in 1919 in Vienna and studied physics and mathematics at the University of Vienna. He received his PhD in experimental quantum physics in the group of Andrew White at the University of Queensland in Australia in the 2016. He was in photonics, and then after he moved to Scotland to do a postdoc in the University of Heriot-Watt, still in photonics. Then he moved as a Erwin Schrödinger fellow in the 2018 in the group of Rainer Blatt, and already there starting what he now is an expert is in ion traps. And to show the quality of his work, he received an ERC starting grant in 2022 to study ion traps, and specifically what he's going to talk today is about this trap ions qudits, not qubits, but qudits. So please, Martin.
Thank you very much, Enrique. It's my pleasure to be here, to be able to tell you a little bit about the things we've been doing for the past couple of years. We've been trying to develop on a theme of trying to improve the efficiency of quantum computing, quantum information processing, and in particular, quantum simulation, which will be the focus of what I talk about today. And the way we try to do this is by getting rid of these old notions of binary information processing and taking everything that we have, all the resources that our quantum computing systems give us to do information processing here. Yeah. So you might think of this of leaving the black and white world of binary information behind and bringing color into this by using qudits rather than qubits. Now, since we have a bit of time, I'll try to give you some idea how this works, give you a bit of an overview. Please, if there are any questions, just interrupt me. Makes it easier than having to wait until the end. So let me get started by setting up the scene here. The basic idea is we're using trapped ions. That's how our artists think about it. Lots of shiny balls on the line. So we have a chain, in our case, a chain of calcium-40 ions. Now, calcium-40 is one of the simplest ion species. You don't have nuclear spin. So you have very simple level structure here. And that's basically what you see in many cases. You have two important transitions here. One is this long-lived transition where you can encode your quantum information. And the other is this short-lived transition that you can use to read out the quantum information, right? And typically that's where we used to stop explaining. We just say you put your 0 state in the ground state and your 1 state in the excited state, and so you have a qubit, and you can do your calculations with that. When you look a bit closer, you see that under a small magnetic field, you get Zeeman splitting of these levels. And so you actually have 2 ground states here and 6 excited states. And when we do quantum information processing with qubits, we pick 2 of these states, and typically we pick these 2 here for convenience, and they also tend to be quite stable. And we encode our qubit here, right? But now there is an important thing to note, right? We have all of these states and we can control all of these states, so we might as well use them for computing. And the intuition here is you could do this classically as well, right? And in fact, in the very early days of classical computers, people have experimented with what is called multi-valued logic in the classical scene. And have actually built devices that encode trits in particular, so 3-level systems. And interestingly, this is now coming back in the past 5 years or so. There is a renewed interest in doing this on the classical side. But the story is very different. Yeah, and this is what I think is important to appreciate here. Classically, I can really, in principle, stick with this picture, right? I can say I bunch these two states, my ground states together, and I call this a 0, and I bunch my excited states together, and I call this a 1. So I can do coarse graining, right? And this coarse graining is what gives you a lot of robustness, because you don't need to keep track of what exact state your ion is in. So you gain this robustness, right? And classically, you set 2 voltage levels, right? And if it's below 1 volt, it's a 0. If it's above 2 volts, it's a 1. And this coarse graining makes it very natural to use bits, right? As the simplest unit of information. You bunch as many states as possible together to get a certain robustness. In the quantum setting, this is exactly what we cannot do, right? We always need to know where exactly our quantum information is. Otherwise, we suffer decoherence, which means already to work with qubits, we need to control that whole Hilbert space. And if we have that control anyway, we might as well use the resources. The overheads are then very small to go and say, I'm not just ignoring all the rest and focusing on these 2 states, but I just use all of them for information processing. And this will be the setting for the rest of this talk. We want to see what we can do with these resources. Now, this is our ion. The ions, as you can see, they're sitting here in a common harmonic potential. And this is another tool that has been used for a long time, and we will use quite explicitly here as well, is a harmonic oscillator degree of freedom that you get when you put all these ions in the same trap. They feel each other, so you have this quantized motion that you can use as a bus for quantum information. And we'll get back to that in a few minutes. Now, to bring everyone to the same page here, I want to talk briefly about how we manipulate these qudits and what is different to qubits. Yeah. So the simplest thing, what you can do is you pick 2 states, you drive them resonantly with a laser in our case, depending on the ion species and the levels. This might be microwaves or lasers. In our case, this is this laser. And when you drive this transition directly, what you're doing is in that 2-level space, you're inducing rotations on the blosphere around an axis in the equator. And you have your laser amplitude and phase to control the rotation angle and the phase of that rotation. Now, you can do this in the trapped ion platform quite easily, either with a global laser beam, and that is relevant if you want to do kind of analog simulation type experiments, or you can use addressed laser beams that are focused on the individual ions, and that gives you digital control. Now, this is the qubit picture. When we go to qudits, we now have this larger Hilbert space here, and you see the errors are already there. The coupling, our natural coupling, using that same laser we have used for the qubit, gives us a coupling between almost all of the ground states to the excited states. And now the good news here is, as long as you have a coupling map here that lets you connect every qudit state to every other qudit state via some path, you can find an efficient decomposition of an arbitrary local gate into these 2-level rotations, with at most a quadratic overhead. The other good news is that the rules we know from qubits still hold, in the sense that in order to build a universal gate set for a qudit device, all you need is Clifford gates and a T-gate. So these are the things that we know from qubits. They still hold. So this is our starting point. The first thing to check is how well can we actually control this, right? There's a couple of additional effects that come into play when you go from qubits, so from like a real 2-level system to a multi-level system. There are very basic things that, for example, when you do such a rotation, you're not actually doing an X rotation, but you're doing I times X. So you get lots of additional phases that we used to consider global phases, but they're no longer global because you have spectator levels that measure all these additional phases. So it's a lot more to keep track of. There's also technical phase shifts, right? When you apply a laser beam, you're shifting the energy levels of all the energy levels in your atom. If all you have is a qubit, you don't notice that, but once you have spectator levels, you do notice these things. So some control overhead in order to check that this can be controlled well. What you can do is such a randomized benchmarking experiment where you apply a random sequence of Clifford gates. I assume many are familiar with this by now. Take a random sequence of Clifford gates, you invert it in the end, which means you get back to the starting state, and then you check how well you recover the initial state. And that gives you a measure of average error rate in these Clifford operations, which you get from the slope of these lines. Now you see, as you go from dimension 2, 3, 5, this gets worse, but it gets worse in exactly the right way, namely with this quadratic overhead that we've seen, so that we get from this coupling structure. So if you now look at the error rate per laser pulse, per like fundamental control operation, this is constant. This does not depend on the dimension, which means all of these additional effects that come in from the multi-level structure is something that we can control very well. So this is local operations. Things get much more interesting when you now move to entanglement. Here again, the good news is just like for qubits, any entangling gate is fine. So you just pick one that you like and you get a universal gate set. The bad news is things that we're used to from qubits don't necessarily hold anymore. So in the case of qubits, it doesn't matter which gate we choose, they're all equivalent. Right? You might have a C0, or you might have this ZZ gate, or you might have a Mermer-Sørensen gate that the trapped ion community likes to use. And they're all equivalent up to some local rotations that you tag on. Now that's no longer true when you have spectator levels. So in particular, this equivalence between the Mermer-Sørensen and the C0 gate doesn't work that way anymore, which is a bit annoying for us. And in general, there is a lot more freedom in choice of entangling gate now. All entangling gates are universal on like the theory level, right? But in practice, it can make a big difference which kind of entangling gate you choose, because I have infinitely many that are not equivalent up to local rotations anymore. So you need to make a choice, and this choice will affect the efficiency of your implementation quite a lot. Now to see this, we can look at two extreme cases first. The one thing is, say you have two qudits, and we make it easy in dimension 3, but you just want qubit entanglement. You want to make a qubit Bell state in there. So you pick something like a C0 gate that you're embedding in a higher dimension Hilbert space, you get that kind of entanglement. You can see that combined with arbitrary local gates, this is universal. But it's maybe not the most efficient to create a lot of entanglement. So for example, the other extreme where you want the whole Hilbert space entangled, you can get there by using this kind of interaction, but it's not the most efficient way to do it. And vice versa, right? You can take this kind of entanglement and combining it with local operations and more entangling gates you get over here, but it's unnecessarily expensive. Now, in terms of how we actually do this in the experiment, I don't want to go into the technical details here. We can discuss that later if anyone's interested. But just for the intuition, if you want to create what we call here subspace entanglement, the way you can do this is by driving directly one of these transitions. Here with the Mermer-Sørensen type interaction, but you're directly driving one of these two-level transitions with an entangling interaction, and that allows you to create entanglement exactly in this subspace of two ions now. Also here, we can show that all these additional effects that come in from having spectator levels and so on can all be controlled, and you get actually effectively the same performance as you get for a qubit platform. Now on the other side, if you want this genuine qubit entanglement, what you can do is, for example, drive here a Farhoff resonant transition which couples this whole manifold to this whole manifold, and that now allows you to create genuine qubit entanglement. You entangle the whole Hilbert space, and the nice thing is you can do this with just a single control parameter. It doesn't depend on the dimension of your system. So you have no control overhead in scaling from 2 states to 3, 4, 5, 6. So So this makes it very convenient to actually do in practice. Now, these are two extreme cases. I also want to talk about one kind of intermediate case, which is mixed dimensional systems. And this is something we'll encounter a lot in like the quantum simulation context, which is in particular when you're thinking of digital simulations where you have this capability to mix different constituents here. And we'll come to a nice example of this in the end. But here we say we have two systems of different dimension. We want to entangle them. And a nice way of doing this is by building on some of the old Sirac-Sola ideas of using the motional mode here explicitly as a quantum bus. Yeah? So in this case, we want to realize a controlled unitary operation. And the way you can do this is on your control ion, you pick the state that should control the interaction. If the ion is in this state, you're injecting here a phonon into the motional mode. And then conditional on that phonon being present in the motional mode, you do a unitary on the target ion. And then you remove that phonon again out of the motion mode. Yeah. So you're explicitly here using the motional mode as a bus. You're using only local interactions. And nowhere in this scheme did you require to know the dimension of your system. Yeah. So this is inherently agnostic to the dimension of the two systems. It's a very flexible approach to design here interactions for these mixed dimensional systems. Yeah. And this is kind of roughly what you get out there. Okay, so this is for gates. The last thing is the readout, which is not completely trivial because the way we do readout typically is we are scattering light of this fast decaying transition. And then if the ion is bright, it's in the ground state. If it's dark, it's not. So this is fundamentally a binary thing. In order to get around this, what you can do here at the example of a 4-lever system is you first put all your information up in the excited states, then you take a picture, and now you know if it's bright, it was the 0 state, if it's dark, it was something else. But the states up here are not perturbed by this readout operation, because they're not fluorescing, they're not scattering any light. Which means if the ion was dark in this first state, in this first readout, you just go in and swap these two populations and measure again. And then check, was it in a 1 state? And if not, you go in and check, was it in a 2 state? And so in one run of the experiment, you can just sequentially check all these states and do the full readout using these binary bright-dark distinctions. That has a small overhead, right? We need to do repeated readouts. Most of the overhead actually comes from the fact that the camera is quite slow that does the readouts. So this is kind of technical limitations. But even with that, you get about 1% readout error in the worst case for a 7-dimensional system. Yeah. And this can still be improved by an order of magnitude with some faster tools. The other thing to note here is it does limit you a little bit in your accessible Hilbert space because this second ground state needs to be free during the readout. Otherwise, you couldn't distinguish these two states. Yeah. So that's why we are limited to 7 states here instead of the 8 that we could have. But if this is really a limitation, there are other ion species that can do 25 or more states. So you can still push this if need be. Good. Then the last thing to say about the experiments here is, of course, things don't look like this anymore. This are the scary pictures we keep for our theory friends. But in practice, the labs are cleaned up. Now you can integrate these things into nice 19-inch racks here. So full trapped ion quantum computer can be in 2 of these racks. One contains like all the optics. Another contains then here the trap module. This is kind of how the latest generation ion trap looks like. Yeah. And in the next stage, these things can then be integrated in kind of HPC environments quite neatly. Good. So to summarize this, this is the gate set we're dealing with. You have arbitrary local gates. You have different kinds of qudit entanglement. And this is not all that can be done. There is a lot more to be explored here. One thing I want to mention at this stage we developed together with Munich here a bit of a software framework, which is a qudit extension to include qudits. So if you want to play around with this, want to see how your algorithm would perform when you write it in a qudit language, this is a nice tool to do this. It includes a simulator platform that can do reasonably complex circuits. It includes essentially this gate set here, plus some noise models, so you can play around with this. There are some initial steps towards a compiler, but much more work is needed there. So if anyone is interested in compiling challenges, this is certainly something that is quite rich. Compiling is already hard for qubits. It does not get easier for qudits. But if you find good ways to exploit this design freedom, you can gain a lot of efficiency. Yeah. And that's the last thing here. These entanglement structures and this ability to design different interactions. This is something that we like to explore. For us, this is a big playground, right? We want to build new interactions. If anyone has a problem that they want to study with a quantum device and you think this naturally fits into qudit paradigm, but my interactions are not like this, then have a look. Maybe these interactions can be generated natively, and then you get a lot of efficiency. And this is really about tailoring your device to the problem to get the most out of it. Okay, that is so much for the boring overview part. Now to the applications. There is two classes of applications I like to distinguish. One is if you want to really work with qubits, but you know that your device has a larger Hilbert space, and you want to see how you can use that larger Hilbert space with kind of minimum effort to gain some advantage in your qubit-based implementations. This is what I call qudit enhanced QRP. This essentially came out of these ideas that you could improve the efficiency of gate decompositions by using auxiliary states, you doing the same function as auxiliary qubits might do, but with the advantage that you don't require extra entanglement and you don't change the connectivity of your device if you use additional levels for auxiliary tasks. Yeah? And that can improve gate decompositions. Another thing that we've played around with is reducing crosstalk errors. Yeah, crosstalk is still an issue in many quantum devices where you want to talk to qubit 7, but you're talking to qubit 8 as well. Way to get around this is by simply encoding neighboring qubits here in different subspaces. Then they're not resonant to the crosstalk, and you get pretty much completely rid of it. That can have quite a significant impact on the performance of the device. Last thing in this direction is measurements. Characterizing our systems, this is something we always have to do. And typically, we do this by performing lots of different Pauli measurements. Yeah? But this tends to get quite inefficient fairly quickly because there are exponentially many Pauli measurements I can choose and often have to choose depending on what I want to characterize. A way around this is by performing a measurement that looks like this. It's called a symmetric informationally complete P of M. So it's a 4-outcome measurement that contains the full information about your quantum state. Problem is, you can't directly perform that on a qubit, but you can perform this kind of measurement if you have a 4-dimensional Hilbert space. And all you really need to do is at the end of your computation, you expand your Hilbert space from qubit to q-quad using some simple local operations. There's no entanglement involved, not a lot of control involved. And then you can embed this measurement and you can turn this into a projective measurement in a 4-dimensional space. You can directly measure that. Then you have a single measurement setting for a large register of qubits, no matter how many qubits, right? And you just run this measurement. You can do all the data analysis. Since this is then kind of a randomized measurement procedure, you can use classical shadow techniques to do data analysis in real time. And then just stop the experiment when everything is converged. Yeah. We've tried this out with something like 8 qubit states that we characterized, and you see that you can, in many cases, fully characterize such an 8-qubit system with fewer shots than 1 per Pauli basis. Yeah. So before, standard techniques have even taken 1 data point in every Pauli basis. This one is already done. So this can give you quite significant advantages in terms of measurement times with almost no overhead on the classical control side. So much for that. This is when you want to use qubits and want to just enhance your qubit-based methods a little bit. But now for the rest of the time, I want to focus on native qudit applications. So what I mean by this is that you're really using your full Hilbert space to encode information and process information. The first thing that typically comes to mind here is spin-1 physics. That's the simplest way to get there. Enrique, there is a question.
Yep, I have a question before you go to this more about this quantum simulation, about this quantum enhanced point that you were mentioning there. It's about the I don't know if you mentioned or you can say it in a bit more detail, possibilities of doing quantum error correction with this qudit enhanced quantum information processing. If you're studying these things, which are the pros, which are the cons, and yeah, if this can be robust. So yeah, having a qudit instead of qubits and all these things.
Yeah, there are interesting ideas how you can do this. I mean, an old example of this are GKP codes where you encode a qubit into either an oscillator or a large qudit, and you can then do the error correction essentially within your Hilbert space. So you get redundancy, not from adding more information carriers, but from having a larger Hilbert space and like encoding information in a small part of a larger Hilbert space. Yeah. And that's an interesting and active area of research at the moment to see what errors you can protect against and how good this can work. Yeah. Exactly. Okay.
Thanks.
Then spin-1 physics. So this goes back to here the Heisenberg chain. So back in the 80s, when Haldane noticed that if you take a Heisenberg spin chain, there is a fundamental difference in the behavior between integer spin and half-integer spin, where the integer spin shows topological properties, while the half-integer spin does not. And I find that really interesting because this is not a quantitative change. This is really a qualitative change in behavior by going from a qubit to a qudit. So this is something that, of course, caught our interest working together with Enrique. Him. So we want to study this natively by encoding each of these spin-1 particles into one ion, one qutrit in our language here. The way people typically look at this model and study this model is by using a relaxation here. It's called the AKLT model. So you have the same Hamiltonian with some perturbations. And when you look at this can be shown to be in the same phase as the ground state of this Hamiltonian. But you can represent it in a nice way, which is as a chain of coupled spin-half particles, which are projected on the links here onto a singlet. Now, this is not what we want to do, but it's instructive to look at this because you very clearly see what happens here on the edge. There is a spin-half left over. And so this is one of these nice features of topological systems, that you get the spin fractionalization on the edge. You have a spin-1 particle, but you get a spin-half degree of freedom on the edge, which is something that is not easily possible because you can't take a spin-1 apart into a spin-half and the rest because it's dimension 3, so it's indivisible in that sense. Yeah. So the spin fractionalization effect is something interesting to study that occurs then once you have these integer spin models. And so when I look at this, directly using spin-1 particles, not doing this single projection, which can be quite inefficient. And so looking at this chain, you see that this can be represented, people have seen that this can be represented as a matrix product state. it allows for this nice sequential preparation scheme where you add an auxiliary system that you sequentially couple to all of these spin 1s. And that allows you to create here the ground state of this Hamiltonian, which you could then adiabatically transform into this one, but they are very close. So for the small systems that we looked at, there is really no difference. Now, having made that state, this of course is highly scalable. Yeah, you just keep adding particles and couple your cavity sequentially to all of these. Having made that, we want to look at the properties of these states. And so the first thing you want to look at here is the correlation properties. Yeah. So first, you want to see there is no local order. So you measure all the local observers. Here we have the distance in the chain and the expectation value of local observers. You see, except for the two edge qubits, this is essentially all 0. So there's no local order. You can also look at the correlations, and you see these correlations fall off really quickly with distance in that spin chain. But if we look at the string order parameters that define this topological phase here, they are consistently non-zero. So you see, and they are defined over the whole chain, as you see here. So you have this non-local string order while having short-range correlations and no local order. This is the hallmark feature of these symmetry-protected topological phases. So this you see nicely here in this Haldane phase. So having that, we can now look at the spin fractionalization and this half, so spin half degrees of freedom living on the edge of our spin 1 chain. And since the correlation length is not 0, you have to take into account 2 of these edge spins. And so in 2 of these spin 1s, you have the spin half degree of freedom, which you cannot drive. So you can drive Rabi flops here. You can define the spin half like Lie algebra, for the SU2 algebra. You can drive these Rabi flops by acting on the edge. So you're driving these qubit Rabi flops by acting on these 2 spin 1 particles. Yeah. You can do the same thing. Since this is the topological phase, you have your bulk edge correspondence. So you can do the same thing by driving the whole bulk. And you again get the Rabi flops of the edge qubits. Nice feature of these Rabi flops here is that the contrast is independent of the system size. As we increase the system here, you see the overall fidelity in our state preparation going down, but the contrast of these oscillations is constant. And this is actually only limited by the operations we do to drive the oscillations, because they are quite complicated because you're acting on 2 spin 1 particles. But this is the only thing that limits the contrast here. Yeah, the overall fidelity of the state does not affect it. So this is nice to see. And then in order to connect this all back to the quantum information world that we are more used to, we also looked at another state in this same phase, which is the qubit cluster state. And you now see that this has very similar properties. You again get short-range correlations, and the cluster state, of course, has a long history in like measurement-based computing, quantum repeaters, and so on. Yeah, so this kind of makes the connection between the solid-state physics of your Haldane phase and practical applications in quantum information. So you see with this cluster state, again, very short-range correlations. You get the edge modes. Here you see actually, here we wrote down the operators to drive the edge modes because this is qubit that is easier to write down. They act globally on the whole chain and drive these qubit edge modes here. And again, you can create long-range entanglement on the edges of your cluster states, despite having short-range correlations. So this reveals again your hidden long-range order in this system. Okay. So that's it for spin 1 physics. Now, I want to come to the last topic I want to discuss here, and that's now gauge theory simulations. And here we come back to these mixed dimensional systems, as you see. But the reason why we were interested in gauge theory simulations, I'm sure most of you know, these gauge theories underpin kind of the standard model and our most basic understanding of physics, right? You have fermions, matter fields that interact with gauge fields, and these are typically highly quantum theories. In many cases, you can't do perturbation theory because things are strongly coupled. You get sign problems. So they become very challenging for classical computers to simulate, which, of course, is something that is interesting for us because that means there is something that we can probably contribute. So we want to study this. And, of course, we want to start with the easiest one. So we look at quantum electrodynamics. We all know that you have charged particles and antiparticles. That's your matter fields. They interact via the electromagnetic force, which is your gauge field. They can annihilate each other and leave some energy behind, but they can also spontaneously be created out of the vacuum. So you can spontaneously, out of a strong background field, create a particle-antiparticle pair. And it's called the Schwinger mechanism. And this is something very fundamental, right? This is the reason why the coupling strength in particle physics depends on the distance that you're probing, for example, right? If you have an electron sitting somewhere, the closer you get to the electron, the stronger the field becomes, and the more likely you are to create particle-antiparticle pairs that then kind of align with the electron and shield the electron. So what you experience of that electron depends on how close you get to it. Yeah, these are very fundamental effects that are difficult to see directly because the energies involved are very high. But for us here, we can tune our energies. It's just a parameter, so we can see if we can observe this phenomenon in the quantum simulation. Now, the first approach, of course, you go to 1D, and this has been done many years ago. Very nice experiment here where they looked at 1D QED, so you put your particles on the line. The way this is typically done is you discretize space to a lattice, and then on like the odd lattice sides, you put either antimatter or vacuum. On the even lattice sides, you put either matter or vacuum. So you have naturally qubits sitting here on these sides. Then you have the gauge fields in between on the links of your lattice. Now you can easily convince yourself that when you are in 1D and you place charges on the line, there is no freedom left for the electric field. Now you can determine the electric field configuration by the charge configuration. So you can get rid of those. And that was the trick that was used in these 1D simulations here in 2016. And then you can measure, you can observe the dynamics of this model. In particular, what you want to see here, here on the horizontal axis, you have time. On the vertical axis, you have mass of the particles and antiparticles. And then you start, like the colors are the particle density. So you start in the vacuum here, black. And then as time evolves, you see particle pairs are being created. And then as the density goes up, they start annihilating again. So you get an oscillating behavior in your particle density. Yeah, this is very nicely seen here in Werther. If the particles are heavier, it's more expensive to create them, so the densities go down. So you can see this dynamics very nicely. The problem, of course, is if you want to study real-world physics, then you're missing a few things here. The first thing you're missing is the gauge fields have no dynamics. So that's something that's different in 1D because the lines, the charges on the line determine the gauge field configuration directly. The other thing is you don't have magnetic fields because magnetic fields need loops. You don't have loops on a 1D line. So the physics here is really quite different from 2D and 3D physics. So if you want to get to simulating nature, we need to go to 2D and eventually 3D. Difference between 2D and 3D is not so big anymore, but 1D to 2D is a big jump because you need to include magnetic fields. So going to 2D, that's how it would look like. You again have your lattice. On the lattice sides, you have matter and antimatter, depending on which lattice side you're looking at. and on the links, you have your gauge field. Yeah. And the gauge field looks like this now. Here, the gauge field has non-trivial dynamics, so it needs to be included explicitly in your simulation. And what you need is zero field, or the field pointing one way or field pointing the other way. And then you can have multiple excitations of that field. So you get this infinite ladder in both directions that you need to simulate. And so in order to be able to do that, you need to truncate this gauge field somewhere. Whether you simulate classically or quantum mechanically, it doesn't matter. You need to truncate somewhere. And now the important thing to notice, which also motivated us to look at this from the qudit perspective, is that the minimum truncation you can do is dimension 3 if you want to maintain the physics of quantum electrodynamics here. Because you need to have zero field, and you need to have field pointing in one direction and a field pointing in the other direction. And depending on the physics you want to see, you might have to truncate in dimension 5 or higher. Okay, so putting all of these things together, this is how I imagine this to look like when you simulate kind of lattice gauge theories in the long term. You end up with something low dimensional sitting on your lattice sites, which is your matter fields, and something high dimensional, which is your gauge fields. And so for us, having these native mixed dimensional entangling gates makes it quite natural to simulate these systems. The other thing you need is the 3D geometry in the long run, because you want to do real-world physics, which is 3D. Also here, it helps to have this all-Tor connectivity that the ion trap gives us, so we can build any geometry we want by how we choose to entangle the ions. Okay, so this we have. Let's look at that Hamiltonian. There's a couple of terms. I just want to quickly introduce those without much mathematics. You have electric field energy and magnetic field energy. The magnetic field energy now, of course, is the new thing in 2D. And you see, this is kind of a general feature, they scale in opposite ways with the coupling strength G. And this has important consequences that we'll see in a moment. Then you have some mass term of the particles, and you have this kinetic energy term. And the kinetic term is the one that couples gauge fields and matter. So this is the interesting term that you want to study when you look at this pair creation dynamics. And then there's a Gauss law, which is the same as kind of continuous version of it. So that the field that's go in has to come out again. Okay, so we want to start here with looking at equilibrium properties. So we take the simplest building block here, which is one plaquette, 4 matter sites, and 1 gauge field. In principle, you would have 4 gauge fields here, but it turns out that 3 of those are redundant. You can get rid of them. You need to keep only 1. Encode that in the ions, like we already said. And then we want to run a variational algorithm to find the ground state. So we have a circuit, quantum circuit here, with parameterized operations. At the end of the circuit, we measure the energy. We feed that into a classical computer, which optimizes the parameters for our circuit. And we run this feedback loop until we found the lowest energy, and we call this the ground state. Yeah. A bit of a comparison. Although we only have 1 qudit in here, you see you already gain about a factor 4 in entangling gates. Yeah? And the more qudits you have, the more you'll save here. We run this optimization. You do this in blocks, but you can actually reuse some data, so you can optimize for all values of the coupling strength at the same time, which is very useful because these variation algorithms tend to take a long time. So being able to optimize for all coupling strengths at the same time makes this much more efficient. And this is what we want to see in the end, how the system behaves at different values of the coupling. So we prepare the ground state, and for the ground states at different coupling strengths, we then measure the plaquette expectation value, which looks like this. Looking at this in some more detail, plaquette expectation value is interesting because this is the magnetic field. Yeah? This is a true 2D quantity. This is the thing that doesn't exist in 1D. And this is also something that has a lot of relevance in the particle physics case. Yeah, so this is related to the running coupling and things like that. So it's a relevant quantity to study, and we study that for different values of the coupling here over 4 orders of magnitude. Yeah. So you can look at different cases here. On the far left, you have the strong coupling regime, where everything is very expensive. So nothing really happens. You don't create particle pairs, because it's too expensive. On the other side, you have the weak coupling regime, where you have lots of electric fields and magnetic fields, but everything is so low energy that it decouples. And again, not much interesting happening. But in the intermediate regime here, you see now that you have a competition between pair creation terms and field energy terms that drive your plaquette expectation value up in the intermediate regime. Yeah. Compared to here, the dashed line is if you did not include matter. Yeah. So the presence of the matter really changes the magnetic field configurations. You have these dynamic and magnetic fields that are created by the particle pairs in that system. Yeah. The other thing that you see here is we truncate in dimension 3, and the data lies very nicely on the ideal theory line. So this is enough. We don't need more than dimension 3 for this case, because the matter has a regulating effect. It prevents too large excitations of the gauge field. So in order to explore this truncation, we get rid of the matter. We take the same Hamiltonian as before, but without the matter fields. Now what you see is in the strong coupling regime as before, you get very low excitations because everything is expensive. As you go to the weak coupling regime, you populate all these electric fields energy levels. So your resource requirements explode for the simulation. This is not good. A way around this, developed by our collaborators here in Waterloo, is to switch to a magnetic field basis where it behaves the opposite way. So it's well controlled here in the weak coupling regime. It's poorly controlled in the strong coupling regime. And intermediate regime you have to see. Yeah? So now you have good representations for the extremes. You need to see what happens in the intermediate regime. We do the same thing as before. We now take a pure gauge plaquette. Here, slightly different representation, but you need to keep track of 3 gauge fields in order to capture this system. So we again have our variational circuits now up to dimension 5. Here you see the story is already a bit different. If you were to do this with qubits, it would cost you a factor 5 in register size and more than a factor 10 in gate count. Yeah, so here you're really playing to the strength of this qudit platform. Same as before, we now prepare the ground state using a variational algorithm, look at the plaquette expectation value. What we notice here is the red lines, which are the electric representation, fit really well here in the strong coupling regime, and the blue, which is the magnetic, fits very well in the weak coupling regime. The intermediate regime, it's a bit different. You see the light-colored data, which is the dimension 3 truncation, is not good enough. Yeah, there is a big gap here between the blue and the red curves. But as you go to dimension 5, this gap closes. Yeah? So you get a pretty good representation already in dimension 5, and dimension 7 is then, in theory, pretty much perfect already. Yeah? So you can see how increasing the truncation now helps here to improve the accuracy of your simulation. Okay, and very briefly, the last thing, you also want to do dynamics and look at the things we saw before in 1D. So we go back to our plaquette with gauge fields and matter. We drew a Trotter-Suzuki decomposition, which means you take your Hamiltonian, take the 4 non-commuting terms here, and apply them stroboscopically after each other for a short amount of time. So you see in the representation we work with here, the magnetic field energy particle mass is basically trivial. Electric energy is a bit more complicated. The pair creation term, of course, is the tricky one. Here you really have this dynamics. You get 2 vacuum sites. You get a spontaneous creation of a particle-antiparticle pair, and the gauge field has to change accordingly so that everything matches again. Yeah. But you can do this, and then you can look at here the matter dynamics. Yeah, so this is what we saw before with the particle number density. You start in the vacuum state, and then pair creation processes drive the density up. Then annihilation kicks in, density goes down again, and you get this oscillating behavior. On the side of the gauge fields, looking at the plaquette expectation value, you see a similar thing. Initial pair creation processes drive up the gauge fields. You get magnetic fields, get a spike, then they drop again, and you get interesting oscillating behavior. So there's very rich dynamics in here that needs to be explored a bit further still. But you can already clearly see this characteristic behavior, this oscillating behavior, as the vacuum decays essentially into a stable state. Okay, so with that, I summarize. I hope I showed you that we have these capabilities, not just us with trapped ions, but most kind of hardware platforms nowadays, to go beyond qubits and really use that large Hilbert space we have available. Particularly in the case of quantum simulation, this is something that is very natural and can be very powerful if you have the right kind of interactions. What we would really like to see at this stage is more algorithm development for such a platform, to see, write your problems in this language, see what is the most natural, most efficient way to implement them, and then try to match the hardware to that. So with that, just left to thank the team who did all the hard work here. Thank you for your attention. I'll be happy to take some more questions.
Thanks, Martin. I don't know if there are questions from the audience. You have some time. Please raise your hands and speak loudly. I have some questions, just maybe while the audience is warming up. First is about the magnetic basis, and the other is about the time evolution. There is a plot that you show there about how it's improving with the dimension of the Hilbert space in the electric basis from d equal to 3 to d equal to 5. But in the magnetic basis, you don't mention so much how you can do this improvement or this one. So about the improvement in the magnetic basis, you didn't mention so much. So what is the dimension of this magnetic basis?
This is also dimension 3 and 5 here. The difference here, so the dashed lines are the theory. The differences are just not as large, also already in theory. Right? Here in the electric basis, you get a big jump, and then the gap is almost closed, so then you don't expect too much. Yeah.
And here is a doubt that I have is because the magnetic basis is a basis of the plaquette. So I suppose it's something non-local because, so when you are changing this basis, you are changing from something local because it's living on the links to something that is living on the plaquette. I suppose.
Yeah. So, I mean, it doesn't necessarily mean that your circuits and everything gets easier, right?
Yeah.
The argument here is only about how many, states do you need in your truncation? Yeah. Because this is, for us, important to figure out how large does the qudit have to be so we can efficiently implement these things. It might well be that the circuits get quite complicated if you want to do like time evolution in that basis or something like that.
Okay. And the last question I mentioned is about this time evolution. You have the plots of the time evolution. If the experiment stop at the middle, here, at the middle of the way, or you just stop it there at pi half?
We did the time evolution until here.
Okay.
Because the dynamics is quite rich, and the trotter errors are significant. So you'll need still quite a jump in gate performance to push this much further out. Yeah. Here the intention was just try it out, see how it performs. It performed pretty well, I think. But you really want to push here, do deeper trotter circuits, finer decompositions to get closer to the real physics there.
So then, related with this, do you use some kind of error mitigation techniques, zero noise extrapolation, or things like this for this, or this is the raw data almost of the experiment?
This is our raw data. You could use error mitigation quite easily actually here by checking the Gauss law, for example. This is something that was also done in the 1D experiment I showed in the beginning. In this case, we didn't bother doing that because the data was nice enough, and we preferred to use the raw data directly.
Okay. Thanks, Martin. Any other question?
Yeah, I want to ask a couple of things. So, just for simple qudits, is there an analog version of the solo Architect theorem? So, I mean, that you can do with simple gates to reach, I don't know, what is the analog of the Bloch sphere here? I can imagine, but you can reach any space, any point.
Yeah, exactly. So you have an analog of all of this. And this is what I meant in the beginning by you need a Clifford plus T gate set to have a universal computation. Yeah, this is very nice. The Clifford gate set becomes much larger. This grows very rapidly with dimension. But it's still, you have these results. They translate, many things translate, not everything, but these important results do, yes.
And for universal computation, I mean, this is for a single qudit, no? I mean, but if you have many qudits, you can do with so what is with just C nodes, or just with two entangling two qudits, and that's enough.
Yes, and it's any entangling gate really. Of course, it's nice if it's a Clifford entangling gate, so like a generalized C node. Yeah. But if you just want a universal set, you can pick any gate. Yeah.
Yeah. But with two qudits is enough, no? You don't need 3 qudits.
Yeah, exactly.
Yeah. And the last question is, suppose I want to do quantum chemistry, no? I mean, typically I have my Hamiltonians written in terms of fermionic operators. Do I gain something by, is there a way to map these two qudits that is more advantageous than two qubits? Or, I mean, usually qubits are very natural because the Jordan-Wigner is the natural thing to do, no? But if I have qudits, what advantage do I have in terms of quantum chemistry or for tackling problems?
Yeah, I think you always need to look at your problems very early on before you do lots of transformations and encodings and writing it in qubits, because then translating it back is very difficult. There are nice proposals coming out of Sydney, for example, looking at chemistry dynamics by having qudits to encode the electronic states and actually using the motion in the trap to encode vibrational degrees of freedom of a molecule or something. Yeah. And so I think there is still potential to use even more of the resources we have in these systems very directly to simulate these systems.
I see. So you see, instead of writing the effective Hamiltonian in terms of fermionic operators, do this before, no? And just tackle the levels of the molecule directly. Yeah, exactly. Okay, so I'm done. Thank you. I don't know if
Alessio? Yeah, Alessio, tell you. Please, Alessio. You are mute. I don't know if you are talking now. Alessio. Are you around?
You have to unmute yourself, Alessio. Oh, it seems that he cannot for some reason. Maybe I'm ready.
Yeah, because before it was not possible to mute. Okay, thanks for the thought. Maybe I lost the first part, maybe you mentioned, but are you planning to go really to a 3D configuration for ions, or you keep your planning working still on a chain?
So for now, we'll stick with the chain, and then things will go to some scalable architecture, which all look to be 2D for now. 3D is more complicated. But since you tend to have all-to-all connectivity, you don't really care about the configuration of your ions in real space, right? This is just how you choose to entangle them. Yeah.
Yeah, but in practice, this also means that when you start connecting farther and farther away, normally you are slowing down, no? So I wonder where are you trying to go in to a 2D crystal in a way also to increase speed for long range connectivity?
So in the current setting, there is actually no dependence on distance at all, because we're working with a common motional mode. So all the entangling gates between any pair of ions are equally fast. If you now work with 1,000 ions, it's going to be a bit more complicated, and then you'll have to look at probably some shuttling based architectures that are emerging. There is some, one has to check what the overheads are there. I think near term, it's not going to be 3D, maybe 2D.
Okay. Thanks a lot.
Any other question, comment? Okay.
No. Hello, can you hear me?
Yes.
Yeah, okay. So I have a question about bell pairs or of qudits, kind of. So could you tell me how what is the biggest amount of entanglement one can have between two qudits, like of dimension d? So I know how it works for qubits. So you create bell pairs. So how does it work for qudits?
This is quite a non-trivial question, actually. You have to define what you mean by how you quantify your entanglement, right? You can look at entropies. You can look at kind of Schmidt rank, which tends to be a good measure for complexity. And the Schmidt rank, of course, scales linearly with the dimension in like a 2 qudit system. The entropy scale more slowly, but it depends very much on your application. It's also not clear anymore what you mean with maximally entangled, right? All these notions get much more complicated. There is lots of different classes of entangled states with qudits, already with 2 qudits. So these questions they're not so easy to define even.
But if I just introduce, like using entropy, for example, entanglement entropy, then there is some state, right? Probably which is has the biggest entropy, like entanglement entropy.
Yeah, one would have to look at probably something like a generalized Bell state, right? Or generalized like qudit state. The thing I showed in the beginning here. This where is it? This kind of thing, no?
Yeah.
Might be something along those lines.
And so with your experiment, is it easy to construct this by starting from a product state and then doing some 2 qubit gate, or could you?
Yeah.
Mm-hmm.
No, these things are fairly easy to construct, yes.
Mm-hmm. Mm-hmm.
There's different ways you can get there. You can build it up out of these pairwise interactions, right? Here you just need linearly many of those to create such a state. You can do gates like this, which more directly creates these states. You can also use these controlled rotations, right, to flip one after the other. There's many ways, but these states are fairly easy to create. But you can, once you go to more than 2 qudits, you can get very rich entanglement structures that are then non-trivial to generate. And then it really depends on having the right kind of interaction to get to that state efficiently.
I see. Thank you.
Any other comment, question? So, if not, yes, thanks again to Martin for these seminars. And in the following days, Javier, you will announce when is going and who is going to be the next seminar, because maybe there is a chances of having a new seminar on ion trap, but this has to be seen. But yeah, in the following days, then you will announce, no, when it's going to be the next seminar.
Yeah, the next seminar is the 5th of May of June, I think. No, wait, Marting for the 6th of May by Benedict Powell. Yeah, but this will be announced at the time. Yeah. Okay.
Well, thanks again, Martin. Okay.
Thank you.
Thanks a lot.